So after that interlude on how dipole antennas work, I want to come back to Maxwell's equations and understand how they imply some unusual facts about the nature of space and time. Okay, so when I told you that light is an electromagnetic wave, you might have naturally asked, okay, well, what is waving, right? So for other waves that you know about, you might think of sound waves, for instance, as a wave that you've heard of. What is a sound wave? Well, a sound wave propagates in air, so there's a bunch of air molecules, and in some places those air molecules bunch up and become more dense. In other places they spread out and become less dense, and they bunch up and spread out, and there's some pattern that repeats, but that pattern moves and translates through the air. So because there's physical objects sitting there that are waving, these air molecules, it makes sense to talk about the speed of sound. By the speed of sound, I mean how fast is this pattern of spreading apart and bunching up and spreading apart and bunching up, how fast does that pattern move with respect to the air molecules, right? Relative to the air molecules. So if light is some wave, an electromagnetic wave, you might ask, what is the speed of light measured relative to? Are there some objects like air molecules that are actually waving in a light wave? So people thought that the answer to this might be yes. After Maxwell published his paper, people invented an invisible substance that fills all of space called ether. So they also called it the luminiferous ether. So you should think of ether as kind of like air or water, right? There's some air-like substance that fills all of space, even out in empty space where there's no actual air. They claimed there was some substance called ether, and light is a wiggling of the ether. It propagates through the ether the same way sound waves propagate through air. Or you can think of the ether as water, and you can have ripples in water waves that travel through the water. So the issue is that if there is such an ether, this makes a prediction, right? So if this ether fills all of space, maybe it has some motion with respect to the Earth. If the ether were like air, you could have some wind, right? The air could be moving. So these arrows indicate kind of the direction that the ether is moving in. Maybe the ether is kind of blowing like wind a little bit down and to the right. And the Earth is moving through the ether. But the problem, or the prediction, I guess, that this makes is that if the Earth is moving relative to the ether, it's kind of like a boat moving with wind. You would expect that when the Earth is moving in some directions, the speed of light would be different than when it's moving in other directions. So this is like if you're in a boat and you have the wind behind you and you're heading forward, then you're going to go faster because the wind is in the same direction you want to go. If you're in a boat, a sailboat, going against the wind, you're going to go slower, right? Because the wind is in the opposite direction. And in the same way, if light is just a wave in this ether, then the direction that the Earth is moving in relative to the ether could change the speed of light, if this were true. It turns out that that's not true. There is no ether. There was a famous experiment in 1887 by Michelson and Morley, and basically what they did is they took a light source, almost like a laser. They split it into two beams using this kind of splitting mirror. So goes in one direction, goes in the other direction, and they could very precisely measure how long it takes the light to go to and back along this path and towards and back along this path, and see whether the time was different. And they repeated this experiment by kind of like rotating the table so that these two paths are in different directions. They did it at different times of year to try to measure whether the Earth's motion relative to the ether changed the speed of light. But in every possible case, they found that the speed of light was the same. It never changes. There's no ether wind, which strongly suggests that there is no ether. Light is not like a sound wave that moves through some medium. It just is. It travels through empty space, through vacuum. And in particular, that means the speed of light is a constant. It doesn't change if you're going, say, towards the wind or against the wind of the ether. It's always the same. Now that's a little surprising. Let's see why that's surprising. In Einstein's famous 1905 paper that started the subject of special relativity, he began with that very assumption, that the speed of light is a constant for all observers. So you always measure the same speed of light, c. His only other assumption was that the laws of physics should not depend on the physicist. That means if I'm standing still and you're running past me at some speed v, the laws of physics should not be different for you as they are for me. You might make different measurements. You can measure things differently if you're moving with respect to someone else, but the laws of physics that tell you the relationships between those measurements must not change. They should be the same for everyone, very democratic. So assumption 2 is fine. This is not especially controversial. But assumption 1 is very strange, and I'll tell you why. Usually we think of speeds as adding. So if I'm on a train going 100 kilometers per hour and I shoot an arrow and the arrow's going 100 kilometers per hour relative to me, if you're sitting on the ground, you'll see that arrow going at 200 miles per hour, right? This is 100 plus 100. And if I'm on the ground and I shoot an arrow going 200 miles per hour, they'll look like they're going the same speed, right? Because your speeds add 100 plus 100. The point is that's not true for light. So if I'm on a hypothetical very fast train going at half the speed of light, and then I turn on a laser, the laser produces light that's moving at the speed of light, the speeds don't add. It's not the case that I add the two numbers the way I did here, 100 plus 100. I don't add half the speed of light plus the speed of light and get 1.5 times the speed of light. That's not what you measure. The person sitting on the ground outside the train sees my laser coming out at exactly the speed of light, the same as the speed of their laser. It doesn't change. Now that's very unusual, and we can derive some very interesting consequences of this pretty easily with just some geometry. So here's a kind of a setup that will make that clear. So we're going to make a clock, a light clock, if you will. What does the light clock do? Well, the light clock has two mirrors, one at the top, one at the bottom. I turn on a light source, maybe a little light bulb or something at the bottom. The light goes up, bounces off the top mirror, and comes back down. And I want to think of this clock as being one tick of the clock every time the light makes a round trip. It goes up and back down, that's one tick. Goes up and back down, that's another tick. That's how I make my clock. So what is the time between ticks? Well, we can use distance equals rate times time, right? The total distance is 2L, because this guy goes up an L and back down an L, so it's a total of 2L. The rate, which is the speed, is c, the speed of light. So the time is distance over rate, which is 2L over c. So that's the time between ticks of the clock, 2L over c. Okay, now I put that mirror on a train. So I put the mirror on a train. The train is moving to the right at some speed v, and I'm standing outside the train. I'm standing on the ground. So since I'm outside the train, what happens when I turn on the light and it's going to bounce between the mirrors? Well, to me, since the light is going up, but the train is moving to the right, to me it looks like the light is traveling on a little diagonal path, right? So it goes on some diagonal path because the train is moving to the right. It hits the top mirror and then comes back down along a diagonal path and hits the bottom mirror. And that's one tick of the clock. So I'm going to use the symbol T prime. Prime just means different, a different time, perhaps, not like a derivative or anything. So I use T prime for the time it takes for this clock to do one tick, up and back. So again, by distance equals rate times time, this guy has to go a distance 2d, where d is the length of this diagonal. 2d is the total distance. C is the same. That was the critical assumption, that the speed of light is the same for all observers. So the rate is the same. So now T prime, the time for one tick of this clock, is 2d over c. And you might ask me, okay, what's d? Well, we can use the Pythagorean theorem. So this vertical leg is L, the distance between the mirrors. Since the train is moving with speed v, in time T prime, the total time it takes for the light to go up and back, the train moves a total distance of vt prime, just by distance equals rate times time, which means that this piece is half that distance, a half vt prime. And then I just apply Pythagoras. Pythagoras tells me that the hypotenuse squared, which is d squared, is this side, L squared, plus this side, 1 half vt prime, all squared. So I get this Pythagoras. Now for some algebra. This will give us an interesting result. So I had a few equations, right? I had T prime, the time between clock ticks when it's on the train that's moving. I had T, the time between ticks when the light clock is stationary. I can rearrange these equations to solve for D and L. So that gives me an equation for D, which is right here, an equation for L. Then I go back to my Pythagoras. This is my Pythagoras. I take the D and plug in D here, and I plug in L here. Right? So I just put in those numbers. That gives me ct prime over 2 squared equals ct over 2 all squared plus a half vt prime all squared. When I square the halves, I'll get a quarter on every term, so I can multiply through by 4 to kill all the quarters. I move this term to the left to collect all the t primes. Then I'm going to factor out to get my t prime, divide by c squared, and then solve for t prime. Now I get the answer. It looks like the time between clock ticks for the moving clock, t prime, is different. It's not the same as t. It's t divided by some number. What is this number in the bottom? Well, v has to be smaller than c. So if v is smaller than c, this is 1 minus some number less than 1. So the bottom is some number less than 1, which means if I divide t by a number less than 1, I get something bigger than t. So that means the time between ticks for the moving clock is larger. T prime is larger, so it takes a longer time for the clock on the train to go between ticks. The clock is slowing down. And this is a famous result called time dilation. So we just showed that a moving clock runs slow. If I look at a clock on a train moving with speed v relative to me, then I will see that clock running slow by some factor. I use the Greek letter gamma for this, but gamma is just this 1 over square root 1 minus v squared over c squared guy. So the clock viewed from someone who's moving with respect to it is gamma a longer time than the proper time. T proper just means the time you would measure if you were moving alongside the light clock, right? So this seems very strange. You would have thought that time passes the same for all observers. But it's actually not the case that time passes the same for all observers. This has been tested. There's this experiment where these people put very precise atomic clocks on airplanes and flew the airplanes around very fast, and you could actually measure that the time passes more slowly for the moving clocks. So this has been tested many, many ways. There's that. It's been tested looking at cosmic muons that come into the atmosphere. It's tested in particle accelerators. So although it's unusual, this is absolutely a true fact about our universe. Time is not absolute. Now this implies something else about length. So let's think about length. Suppose we have two people A and B. Person B is running by at speed v, or you could think person B is on a train, if you like, moving at speed v. Person A is standing next to a stick of length L. So there's a stick of length L as measured in person A's frame. Now I ask the question, how long does it take for person A, or according to person A, how long does it take for person B to pass by the stick? So what is the time between when person B just passes the left side of the stick to when they just pass the right side of the stick? How much time does that take? Well, again, distance equals rate times time. So time equals distance over rate. The distance is L, the rate is V. So person A thinks that, according to his clock, it will take a time L over V for person B to pass the stick. However, as we just saw, if person B is holding a clock, person A sees person B's clock running slow. So person B's clock is running slow, which means the time between ticks is longer. And since it's taking longer to go between ticks, that means person B is going to measure a shorter time, a smaller number of ticks, because the ticks are all longer in duration, right? So person B measures a shorter time. What is that shorter time? Well, it involves this factor gamma again. The shorter time will be the time that person A measured times this number, 1 minus v squared over c squared under a square root, and this whole thing is less than 1. So TB is smaller than TA. But now you could say, okay, well, how long does person B think that this stick is? Well, person B has some time that they measure that it takes them to pass the stick. So person B just uses distance equals rate times time. He takes his speed v, which from his perspective is the speed with which the stick and person A are moving. He thinks they're moving. So he takes their speed v, multiplies it by the time that passes on his clock, and gets a different answer. Person B finds the length of the stick is L, the length that person A finds, times this number, which is less than 1, square root of 1 minus v squared over c squared. So if you are running past a stick, it looks shorter to you. Lengths contract. So this is quite remarkable. So now we've seen that both space and time, distances and time measurements, are not absolute. Different people can disagree about how long an object is, or the duration of some process, how much time elapses on some clock. And both of them are right. No one's making a measurement error. It's just that those values are actually different depending on whether you're moving. So this leads us to the subject of special relativity, which deals with space-time. So really what Maxwell and Einstein are telling us is that space and time on their own don't have absolute meaning, right? Length or clocks can do different things depending on whether you're moving. Only when you stitch them together, when you combine space and time into a new object called space-time, do you actually have real absolute meaning, right? So here I've drawn a space-time diagram, which I won't explain in great detail. You'll draw diagrams like this if you take a class like 8033 at MIT. But the point is just that when a person is running or moving at some speed relative to another person, their space-time diagram have axes, coordinate axes that look tilted, right? They kind of tilt relative to someone else's axes, and those tilted axes mean that the length that you measure might change. This length might be different than the length that you would think something actually has if you are in a stationary frame. So these distances can change. Okay. That concludes our discussion of relativity. So to wrap up, I just want to talk about some big picture principles and see how they relate to magnetism.